So we have 3 lectures coming up on phase diagrams, and let me see what happened here. There we go. So phase diagrams are essential to understanding refractories. So I have a brief introduction to phase diagrams, the phase rule. We'll do some 1-component phase diagrams, and we'll get started on 2-component phase diagrams. And we'll start out with a simple eutectic system, and then next class we'll go over the other types of 2-component phase diagrams. So I've been mentioning that refractory systems are composed of multiple crystalline phases and non-crystalline or glassy phases. And the type and distribution of these phases is going to determine the properties of the refractories. There's also a porosity phase. So we went over different crystalline structures and noted they're mostly covalent and ionically bonded, and the high melting points are due to the strong covalent or ionic bonding. I tried to go over silicate glasses last class and try to show that the viscosity was important, and it's a function of the additions to a silicate type glass, which is the most common in refractories. So impurities lower the connectivity and decrease the viscosity, which lowers a lot of high temperature properties. So the type and distribution of phases is important in determining the properties. And then you can use phase diagrams to estimate the type and distribution of these phases. So we're looking at solids, solid phases, liquids, and vapors that are in contact with each other on these phase diagrams. So there's a few definitions that we need to go over for phase diagrams. The first one is system. That's any portion of a material that can be completely isolated for consideration of changes which may occur when you vary the conditions, which would be mostly pressure, temperature, and composition. So an example of a system, the 2 components, SiO2 and Al2O3, which are common in all the alumina silicate-based refractories from fire clay to high alumina, they make up the system SiO2, Al2O3. A phase is a portion of a system which is physically homogeneous and bounded by a surface. So you can mechanically separate a phase. So another example would be SiO2. It has basically, well, it has more than 3 crystalline phases, but the ones important to us are quartz, cristobalite, and tridymite. So these phases can be mechanically separated in this type of system, the SiO2 system. The components are the smallest number of independently variable chemical constituents necessary and sufficient to express the composition of each phase present at equilibrium. So again, going back to the SiO2 Al2O3 system, SiO2 and Al2O3 are the components in this system. All the phases and reactions that take place are going to be between these 2 materials, SiO2 and Al2O3. There's something known as variance, it's the degrees of freedom. So it's a number of intensive variables, and intensive variables are temperature, pressure, and concentration of the different components. So it's a number of intensive variables which must be fixed in order to define the condition of the system. So we'll go over this and as we look at each type of phase diagram, and it'll become more clear what variance is. But if it's an invariant situation, you have 0 degrees of freedom. If it's monovariant, you have 1 degree of freedom. And if it's bivariant, you have 2 degrees of freedom. So in a bivariant situation, for example, you have to specify 2 conditions, such as temperature and concentration, to describe the condition of the system. Monovariant, you would only have one condition to set, and invariant, you have 0 degrees of freedom, so you don't have to set any of the conditions or variables. And then finally, equilibrium. It's a condition in which the properties of the system do not change as a function of time. And you can reach equilibrium by approaching the equilibrium state from different directions. So the same state can be obtained by approaching this condition in more than one manner, dependent on the variables in the system. And refractory microstructures are such that they're really not at equilibrium. You have pretty much a system consisting of coarse aggregates and a matrix. They're not at equilibrium. In some cases, at very high temperatures, they may be at equilibrium, but for the most part, they're not. So we could be more precise about defining equilibrium. So when the free energy change G is a minimum, that's the equilibrium state. So the external conditions are, again, temperature, pressure, and concentration of the different components. If you change temperature, pressure, or concentration, the system's no longer at equilibrium. It will change to reach equilibrium. So the free energy has to be a minimum. So when G, the free energy equals 0, the system is at equilibrium and it no longer changes. So this is the equation for free energy. G is the free energy, it's the energy that can do work. That equals E, which is the internal energy. That's the energy stored in chemical bonds, plus pressure times volume, P times V, minus T is the temperature, and S is the entropy, and that's the energy unavailable for work. So when G equals 0, we're at equilibrium. So a phase diagram is a graphical presentation. It's basically a map where you, as a function of temperature and composition, and it maps out the phases that are present, whether they're solid or liquid, and you can determine concentrations and percentages of different phases. So it's a graphical presentation of data that gives information about the interaction between the different phases. So some of the information on a phase diagram, well, you get the melting temperature of the pure compounds. You get the reduction of melting temperature for a mixture of the compounds. You get new compound formation due to the interaction of compounds. You also can determine the degree of solid solution. You can get the temperatures where these polymorphic transformations take place that we talked about, displacive and reconstructive transformations. And you get the amount and composition of both solid and liquid phases as a function of temperature. And if you have two immiscible liquids, you can get the temperature where they form. So all of these are important when you're looking at a refractory for a high temperature application. You definitely want to know what compounds are present, how much liquid is present as a function of temperature. Not only in the pure refractory materials as produced, but also these phase diagrams apply when the refractory is in contact with another liquid like a glass or a slag. So you can predict what the reactions are going to take place if you have a refractory in contact with the slag. You can determine if there are going to be any low melting phases that might cause issues and result in corrosion. So phase diagrams are essential for studying corrosion. So there's two ways to make a phase diagram. The oldest method is by X-ray diffraction. It's tedious. So you determine the phases present by mixing the powders. You heat them to a high temperature, and then you hold it for an extended time to make sure you reach equilibrium. Then you rapidly quench it, you X-ray it, and you see what phases are present. So as a function of temperature and composition, you can do this. Requires a lot of different samples at a lot of different temperatures. Again, it's tedious, but it does give a good phase diagram in the end. More recently, people use thermodynamics to calculate phase diagrams. So going back to the free energy, if you know the free energy for all the different possible compounds that can form in a phase diagram, you can calculate the phases from thermodynamic data. And there are a lot of, well, not a lot, but there's numerous programs out there that have all this data that you can calculate phase diagrams. So this is the phase rule. It describes equilibrium. So F is the variance. We mentioned the degrees of freedom. C is the number of components. And then P is the number of phases present. So we'll go over this when we look at the different kinds of phase diagrams. So the simplest phase diagram is just a one component system. So it's going to be pressure and temperature. So pressure is in the vertical axis, temperature is in the horizontal axis. So pressure increases going upward, and then in the direction from left to right, temperature increases. So this is a hypothetical one component phase diagram. You have a crystalline material in this phase field. So this is basically a map. So right in this region is crystals A. This region has crystals B. And then as we go up in temperature, we have a liquid phase here. So there's crystal A, crystal B, and liquid. And at low pressures, we have a vapor phase present. So C is the number of components. That's one. It's a one component phase diagram. So here's our equation. We put in 1 for C. So F equals 3 minus P. So points A and point A and point B. Each one of these, there's 3 phases in equilibrium. So at point A, we have crystals A, crystals B, and the vapor phase. At point B, we have crystals B, the liquid, and the vapor phase. So these are invariant points. So 3 phases are present. So F equals 3 minus P, which is this equation right here. P is 3 for 3 phases, so F equals 0, so it's an invariant point. So any change from points A or B in terms of pressure or temperature will cause one of these 3 phases to disappear. So those are our 2 invariant points on this phase diagram. The lines or curves represent 2 phases. So this curve A to D, there's 2 phases at any point on this curve, but it's the phase transformation between crystals A and B. So it's a polymorphic phase transformation. So we talked about displacive and reconstructive phase transformations. It could be, this is hypothetical, it could be either type, but we have a crystal modification A and a crystal modification B. This curve BE is the curve between the crystals B and the liquid. So it's where the polymorph B melts. This curve FA is the sublimation curve for crystals A. So as you decrease the pressure, that's where you develop the vapor phase. From A to B is the sublimation curve for crystals B. Again, decreasing the pressure below this line results in a vapor phase. And then this curve BC is the vapor pressure curve for the liquid. So below BC, the liquid goes to a vapor. So F equals 3 minus P. So if we're on any one of these lines, there are two phases present, so P would be 2, so F equals 1. So two phases exist along any one of these monovariant boundary lines. So pressure and temperature are dependent on each other. So if you specify one, either pressure or temperature, it's going to fix the other one. So that's a monovariant situation. So again, along any one of these lines, you have two phases present. At points A and B, you have three phases present. And then the single phase fields, well, this whole region for crystals A, this region for crystals B, this region for the liquid, and then this other region for the vapor. They're all single phase fields. So again, F equals 3 minus P. P is 1 because there's only one phase present. So 3 minus 1 is 2. So the variance is 2. So one phase exists in these bivariant regions. So pressure and temperature can be independently varied without changing the phase. So within these phase fields, you can change the pressure or temperature, and you won't change the concentration of A, B, or you won't change the phases, A, B, liquid or vapor. So this is a phase diagram, one component phase diagram for silica. So we'll have a lecture on silica refractories. So pressure and temperature. There are three phases present for silica: quartz, tridymite, and cristobalite. Tridymite and cristobalite are high temperature phases. So three crystalline phases. Each crystalline phase has displacive transformation. So going from quartz to tridymite to cristobalite are reconstructive phase transformations. And then each one has displacive transformations. So alpha to beta quartz is displacive. And then beta tridymite has alpha, beta, beta prime. So it has three crystalline forms, all displacive transformations, and beta cristobalite has alpha and beta. So there's two crystalline forms that are both transformed through displacive transformations. So again, it's a one component phase diagram. So C equals 1. So F equals C minus P plus 2. So F equals 3 minus P when you put in a 1 for C. And something to note on these phase diagrams, if you start out with the liquid, you lower the temperature, say you're at a constant pressure, you should crystallize beta cristobalite, but a silica glass is very viscous, and we mentioned the more viscous the glass is, the harder it is to crystallize. So beta cristobalite may not form, especially if you cool it quickly. So this dotted line represents the metastable state that the liquid is still present. It wants to transform to the crystalline phase. And the same thing with beta cristobalite to beta tridymite. If you have beta cristobalite present, you may follow this other curve. It probably will not transform to beta tridymite because it's a reconstructive transformation. But you can also have metastable alpha and beta cristobalite. And the last one here is tridymite. It most likely not going to convert back to quartz, but it may be metastable, either alpha beta or beta prime tridymite. So I mentioned there's displacive transformations, alpha to beta quartz, alpha to beta, beta prime tridymite, and alpha to beta cristobalite. And we'll go over these in detail when we talk about silica refractories. And these are the temperatures where these displacive transformations take place. So the upper use limit for pure SiO2 is about 1723 degrees C, where it becomes liquid. And then these are the displacive transformation temperatures. So at 573 degrees C, you go from alpha to beta quartz. At 870, you go from beta to beta prime tridymite. And at 1470, you go from alpha to beta cristobalite. So going from quartz to tridymite to cristobalite, they're reconstructive transformations. They're the very slow transformations that take place when bonds are broken, new crystal structures form. So in a silica refractory, you start out with quartz. You want to end up with either tridymite or cristobalite, the high temperature forms. So they're going from quartz to tridymite or quartz to cristobalite, or even from tridymite to cristobalite are reconstructive transformations. I've put another example, zirconia. So again, pressure versus temperature, and this horizontal line represents 1 atmosphere. So again, for C equals 1, you put a 1 here, 1 minus P plus 2, so F equals 3 minus P. That's the phase rule for the one component phase diagram. So there's a region here where we have cubic zirconia, another region tetragonal zirconia, and a third region where we have monoclinic zirconia. So 3 different crystal structures, and then a region here where we have a liquid, and then the vapor phases in the bottom right-hand corner here. So monoclinic to tetragonal to cubic are all displacive phase transformations. And again, you see these dotted lines for the metastable conditions. So it's possible to cool this down from the cubic phase and still remain cubic. And it's possible to cool down from the tetragonal phase and still remain tetragonal. But the arrows indicate that these transformations want to take place, but under certain conditions, you can prevent those transformations. And we'll go over that when we talk about zirconia-based refractories. So the monoclinic to tetragonal to cubic are all displacive phase transformations. And then the last one component phase diagram I have here is for carbon. Again, it's pressure versus temperature. You have a phase field for graphite and one for diamond, and then the liquid phase is over here. So F equals 3 minus P applies again to this one component system. So graphite to diamond is a reconstructive phase transformation. This invariant point here, you'll have direct conversion of graphite to diamond, but that point is greater than 3,800 degrees C and greater than 2.1 million PSI. So high temperature and a very high pressure for this direct conversion. So that's some background on one component phase diagrams. What's really useful are the 2 component and 3 component phase diagrams. So the rest of the time today, we'll start 2 component phase diagrams and finish them up next time. So there are now 3 variables: temperature, pressure, and composition. And this is a 3-dimensional model of what a 2-phase component, 2-phase phase diagram looks like. So now we have a component A and a component B. So we have composition in this direction, temperature in the vertical direction, and then pressure in this direction. So this is 0, and as we go along, and then from left to right, we end up with 100%. So we start out with 0% B, and then 100% B at this point. And then we go from right to left, is 0% A, and then 100% A. So that's the composition axis. And then pressure, this plane is a plane of constant pressure at 1 atmosphere, so this crosshatched plane. So we're dealing with condensed systems, refractories are ceramics, and we're looking at a constant pressure of 1 atmosphere. So we take this plane as 1 atmosphere and we eliminate the pressure component on the two-phase diagram. So if you look at this, this is pressure versus temperature. This is our one-phase diagram, solid, liquid, vapor. And then this one over here on this side for composition B, this would be composition A. So B is a single phase diagram. And then we're connecting the two single phase diagrams to make a two-component phase diagram at 1 atmosphere. So we take that plane out, and the phase rule for condensed systems, we're eliminating pressure. So this was a 2 in a single phase system. It's now 1. So the phase rule is changed. It's F equals C minus P plus 1. So this is a hypothetical two-component phase diagram at 1 atmosphere pressure. So C equals 2. So we put a 2 in this equation. So F equals 3 minus P again. So we take this phase diagram out at 1 atmosphere and it looks something like this. Here's our component A, here's B. So this would be 100% B on the right-hand vertical axis. On the left-hand vertical axis, this is 100% A. And then T, temperature is in the vertical direction. So this is a hypothetical two-component phase diagram with one eutectic. That's the eutectic point here at E. So C equals 2. We put in C equals 2 here, and again, it's F equals 3 minus P. So there are a lot of other lines I put on this phase diagram. These are tie lines. So on this diagram, this is 100% A at this point. So M is the melting point of pure A, that point right there. This is 100% B on this axis. So the melting point of B is N over here. This curve, M, E, N, is the liquidus line. So above this curve, there are no crystals, it's all liquid. So this is a liquid region. This solid line is known as a solidus curve. So that's F, E, G. So we go below the solidus line, it's all crystals present, there's no liquid. So we have A and B present. So below the solidus line, everything is solid. Above the liquidus line, everything is liquid. So in this liquid region, we have one phase liquid present. So P is 1, C is 2, so F equals 2 minus 1 plus 1 or 2. So you have to specify both temperature and composition in this region to describe the liquid. And then the liquid is a one-phase system. There are 2 phases in these 3 other regions. So this is A plus liquid in this region here. This is B plus liquid. And then below the solidus line, it's A plus B. So there are 2 phases in this region. Crystals A, a solid and a liquid. This region, you have crystals B and a liquid. And then you have 2 solid phases below the solidus line, A and B. So C is 2, P is 2, so 2 minus 2 plus 1 is 1. So we have 1 degree of freedom. So you have to specify either the temperature or composition to describe the region in any one of these three regions. And then this point E, that's the eutectic point. So you have three phases present at E. You have the liquid, A, and B. So two solids and one liquid at the eutectic. So C is 2 again for two components, A and B. Three phases present, A, B, and liquid. So P is 3. So F equals 0. So E is one of those invariant points. So any change in temperature or composition will cause one of these phases, A, B, or liquid, to disappear. So these horizontal lines are tie lines. They're isothermal lines, lines of constant temperature. They connect solid and liquid phases. The phase diagram is at equilibrium, so the solid and liquid phases are at equilibrium. So keep in mind that the phase diagram is at equilibrium conditions. So A1, X1 is a tie line, A2, M2 is a lower temperature tie line, A3, M3 is another lower temperature tie line, and on this side of the diagram, N1, B1 is another tie line. So this tie line at temperature T3 connects, the tie line is A3, M3. So that tie line indicates at that particular temperature, you have crystal composition A. So these crystals are 100% A. And then the liquid phase present is this composition here, which is about 62% B and then 38% A. So this tie line represents composition in the range from 0 to about 62% B at this temperature T3. So the composition of the crystals, because we're in the region A plus liquid, 100% A, and then the composition of the liquid is 62% B and 38% A. So we can use what's known as a lever rule to get the relative proportions of liquid and crystals at a particular tie line, so at some temperature and composition. So the lever rule is real simple. It doesn't look simple when you read it, but it's the ratio of the amounts of two phases that are in equilibrium, and it's the inverse of the ratio of the lever arms connecting the respective compositions to the overall system composition. So this is the lever rule again, and this is a more simpler phase diagram. We have A and B, the two components. This is the A plus liquid region. This is the B plus liquid region. This is the liquid region. And down here we have A plus B. So we pick a tie line, A prime, R prime, that's at some particular temperature along the temperature axis. And then we look at a composition S. So it's a composition consisting of A and B. So the percent solid of composition A prime just equals this ratio, S prime, R prime over A prime, R prime. So the solid composition is that ratio. So this tie line is opposite the solid composition A. So it's that tie line, S prime, R prime, over the entire tie line, A prime, R prime. So that's the composition of A in percent. And then for the same tie line and composition, so the tie line A prime, R prime, composition X, we can get the liquid of composition R prime. So this is the liquid composition where the tie line intersects this liquidus curve. So the percent liquid is just A prime S prime over A prime R prime. So this portion of the tie line is opposite the liquid phase. So the ratio of A prime S prime over A prime R prime is the percent of the liquid of composition R prime that's present. So you get the percent of the solid phase, the percent of the liquid phase, and the composition of the liquid and solid phases. Typically, if you ever reach 30% liquid in a refractory system, you don't really have a refractory system anymore. It's unstable. So knowing the percent liquid phase and its composition is important. So we go back to our binary phase diagram A and B with all our tie lines, and we'll look at this composition X. X is 70% A and 30% B. So we'll use the lever rule and go down in temperature and see what happens to the solid and liquid phases. So this composition X is liquid above this temperature T1. So we look at our tie line X1, A1, X1, and we go over point X1. So if we're just above X1, it's all liquid. And the composition of that liquid is 70% A and 30% B. So as we hit temperature T1, which is point X1, we start to begin to crystallize the component A. So A just begins to appear. So let's say small crystals of A start to form. And then we drop the temperature down to T2. That's point X2. Now we have a lot more crystals of A that are forming. The composition of the crystals of A is obviously 100% A, but now the tie line goes over to M2, and that's the composition of the liquid that forms at X2. Now that liquid is now 55% A and 45% B. So we're still at T2, and our tie line is A2, M2, and we're looking at this composition X, which was 30% B and 70% A. So we can get the percent liquid of composition M2, which is again 55% A and 45% B, and we can get the percent of solid composition A, this N component here. So using the lever rule for the percent of the liquid present, it's this portion, X2, called A2 X2, divided by A2 M2, and in percent, that's 30% divided by 45%, or 67%. So at this point, there's 67% liquid present. And then the solid percentage is X2 M2 over A2 M2, which is, this is 15%, and the total is 45%. So 15 over 45 is 33%. So right here, we have 67% liquid of this composition and 33% solid of composition A. Then we drop the temperature even lower to T3, and we're at point X3. So we're increasing the amount of crystals that are forming. But now the liquid composition is shifting along this liquidus line. The liquid is now 37.5% A and 62.5% B. So as A crystallizes out, the liquid is being depleted in the A component. And at X3, we can look at the tie line. So our overall tie line is A3, M3, and the percent liquid of composition M3, this composition here, 37.5% A, 62.5% B. That's simply A3, X3 over A3, M3. This is 30, this is 62.5. So 30 over 62.5 is 48% liquid. So as we go down in temperature, the liquid percentage is decreasing. And then the solid percent of composition A is X3M3 over A3M3. This is 32.5. This one is 62.5. So 32.5 divided by 62.5 is 52%. So the percent solid is increasing. So going down in temperature, we can calculate the percent liquid and solid, and we can see what the composition of the crystal is and the liquid phase. So we approach the solidus line, and again, below the solidus line, everything is crystalline. So if we pick a point, we'll call it T4 plus, just above T4. So we're just above this point X4, so we'll call it X4 plus also. So we're moving down, we're getting a lot of crystal formation here. And that's 100% A, the crystals. And now the composition of the liquid is at point E here. It's 30% A and 70% B. So we'll look at the tie line FE just above this point X4. So the percent liquid, and it's the percent liquid is this composition here, 30% A and 70% B, is F X4 divided by F E. So that's 30 over 70, or 43% liquid, right above X4. And then the percent of composition A, the solid phase, is X4E divided by FE. This is 40%. And then the total tie line is 70%. So 40 over 70 equals 50%. So now we have just above X4, 57% of crystalline A, 43% liquid of this composition, 30% A and 70% B. So then we'll call this temperature T4 minus, that point X4 minus. So we just go below temperature T4 or just below point X4. As soon as we go below the solidus line, we no longer have liquid. All the liquid disappears, and now we have crystals of both A and B present because we're in the AB phase field. So at a temperature just below T4 or at a point just below X4, the percent of composition E is F X4 over FE, which is 30 over 70 or 43%. So the crystal that forms at the eutectic here is 30% A and 70% B. And the total of this combination is 43%. And then the percent of this A here is just X4E over FE. That's 40 over 70 or 57%. So we have these two calculations, and we're at point E where we have this crystal that's forming is two crystals actually, A at 30% and B at 70%. And we know that E is 43%. So you multiply 43% or 0.43 times 30% for A, and then for B is 0.43 times 70%. So A equals 13% and B equals 30%. So just below X4, we have 57% A, and then over here, we crystallize 13% A and 30% B. So if you add 13 and 57 for A, you get 70% A, and B equals 30%. That's exactly where we started. A is 70% and B is 30%. So we have 70% of crystal A and 30% of crystal B. So this point M is the freezing point for A, or it's also the melting point for A. So as we add more component B, we're going down this curve here, this liquids curve. So additions of B lower the freezing point of A. So we have a downward slope on this liquids curve going from M to E. E is the eutectic point. So E is unique because if we're at the eutectic composition, we go from liquid to both A and B at the same time. Any other point along the liquidus line, you crystallize A plus the liquid. E is unique because the liquid completely disappears and you have A and B crystals. And then this point N is the freezing point for B or the melting point for B. And as we add A in this direction here, we follow this liquidus line. It's a downward slope. So additions of A to B lower the freezing point. And again, at the eutectic, it's unique. Both A and B crystallize from the liquid. So the liquid completely disappears, and you have two crystalline phases, A and B. So how does the microstructure develop during this cooling process? If you're at the endpoint A, and if you're at composition A and you cool it down, you're simply going to get a polycrystalline microstructure of A crystals. So this is 100% of A crystals, and this is a polycrystalline structure. If you're at composition B, you're going to get another polycrystalline microstructure of B crystals. And if you're at the eutectic, you're going to get 100% eutectic crystals. So it's going to be alternate bands of A and B. So it's kind of a composite type microstructure. So you're getting two phases, but they form what looks like a composite structure of layers or rods of one phase and another phase. So it's a kind of a unique microstructure. So we go from the liquid to point one. We start to see small crystals, small concentration of small crystals forming. So the microstructure consists of crystals of A in a liquid matrix. And as we go from 1 to 2 to 3 to 4, lowering the temperature, the amount of A crystals keep increasing from 1 to 4. So the crystals are growing in size and amount, and they become larger and larger. So now we have larger crystals in the liquid matrix. And then we cross the solidus curve from 4 to 5, and now it becomes all solid. So now we have these A crystals, the larger A crystals, which are present, and now they're in a matrix of this eutectic microstructure, of this fine eutectic microstructure. So the primary A crystals in a eutectic microstructure similar to this one. So this eutectic microstructure, this could be the composition for the eutectic. It's in a crucible. We cool it, we form a solid. You can see the layer structure that forms. And if we magnify it, you can see the layer structure for the eutectic composition. So that's a common eutectic microstructure, alternate bands of the two phases, A and B. They could be layers, depending on the amount of each phase. They could also be rods in the matrix, but it resembles a composite type microstructure. And why does this microstructure form? How do we get a eutectic microstructure? There's a sequence of events that produce this alternating layer structure. the two phases A and B. So we have our liquid melt. It has the right proportion of A and B to be at the eutectic. So A nucleates and crystallizes. And then, so this is 100% A. So as we crystallize A, the region around A is depleted in component A. So this becomes rich in B. So now we have crystals A surrounded by a melt that's rich in B. And then as that melt becomes rich in B, the B phase starts to nucleate and crystallize. So we start building up this layered or rod-like structure. And this process just continues. So as we nucleate and crystallize B, there's a region around this that's depleted in B or rich in A. Here's another region of B, a depleted region here associated with this crystal B, and an increase in the concentration of A. So next to these B crystals, we start crystallizing A again, and next to the A region, which is now rich in B, we start crystallizing crystals of the composition B. So this just keeps continuing and builds up this eutectic type microstructure. So that's the last slide I have today. So we went over some definitions, the phase rule, one component systems, and we started two component systems, and we looked at this simple eutectic diagram. Next class, we'll just go over all the other types of two component phase diagrams, peritectics, solid solutions, and so on. And then the lecture after that is going to deal with three component systems. So that'll be the background for phase diagrams before we start the refractory compositions. So again, phase diagrams are highly useful. You know your refractory composition, you can exactly tell what happens when you heat it up. And two component phase diagrams are simple. Three component diagrams are a little more complicated. But refractory systems are more complicated in two or three phases. There's a lot of impurities. And when they're in contact with a melt of some type like a glass or a slag, you can also use phase diagrams. So that the compositions get quite complicated. And that's where these thermodynamic calculations come in handy. If you know all your components and the temperature and the type of atmosphere, you can use these thermodynamic programs to predict exactly what's going to be there. So that's highly useful for picking service temperatures of refractories, or highly useful for looking at refractories in contact with melts for corrosion studies. So each time we go over refractory composition, we'll look at the relevant phase diagrams for that composition. So that's what I have for today. Have a good rest of your day, and I'll see you next week. Thanks again.